Hello everyone, and thanks for coming to this presentation. And I hope you are enjoying your last day in San Antonio, ASTRO. This is my first time coming to ASTRO, so it's exciting and also nervous for me. First time for me. So I want to start my presentation with this quote, and it's rather a political quote by Winston Churchill. The more distant we look at the past, the farther we can see in the future. This is going to be my first and my second last slide, and I'm going to relate everything and say that how this doesn't only apply to politics, but it also applies in science. So my name is Makan Farrokhkish. I've been working in Princess Margaret Hospital since 2011. I've been involved in this project since 2011 under the supervision of Dr. Mohammed Islam. And in this presentation, I wanted to introduce IQM as we have been introduced, but I want to deliver my point of view and my perspectives on this project and why we are doing this. Because when people come and ask this, okay, why are we doing this? What's the idea behind this? And I am going to start with a story which will maybe help us to understand why we are doing this. Have you guys heard of TERAC 25? Famous story. So for those who haven't heard of it, TERAC 25 was introduced by Atomic Commissioning Limited, and it was a very complicated and state-of-the-art in mid-1980s. It was versatile. It was top of the technology. They used a double pass acceleration system to accelerate the electrons up to 25 MV. But the devil lives inside details. So what happened with this machine was working, everything was fine, but it also caused a disaster. One of the worst, well actually the worst radiation incidents for the past 35 years of radiation physics. It happened because of this unit. So what happened with this unit was that it was an error called the racing condition in the software. And the racing condition means that the output depends on the speed of or the timing of an uncontrollable events. So what happened with this unit was that when they put the parameters manually in the software, at sometimes for the photon mode, this filter wasn't placed in the middle. It didn't come to this correct position. So what ended up happening was that we treated patients in photon mode using the electron current mode. So we treated the patients in a very high current of electrons without having that filter or that target in the middle. So patients who were gone under treatment, they explained it as being struck by lightning. And unfortunately, 6 people passed away due to massive overdose. So my point with this story is that errors are part of life. They are present, they can happen. We can prevent them, but it doesn't mean that we can eliminate them and totally eliminate them out of the system. So in this story, what happened was that they did a study by Nancy Lemstone. She did a study in 1993. She assessed everything and she said that, okay, this was due to a series of software events. So what happened here was that we got the error caused a bad consequence, and we learned from the error. That's what we did. So why not have a system that, given that the error exists, the error is present, we get the error, but we execute on it right away. So we learn about the error, but we don't have the bad consequences. That's a win-win situation. right? We know about the error, we learn about it, but it doesn't have any bad side effect because we execute on it. And I don't want you guys to confuse this with the Teract 25 novel. It's the best love story unlike any others. I don't know what that has to do. So the question one that I have is, what can we do to detect the error, execute on it before causing harmful damage, and learn about the error? So today we use all these detectors that I'm sure you guys are familiar with to perform pre-treatment QA, and that's because we want to make sure that we deliver the right dose at the right location. And as the treatment models they get advanced, like we were first at static, then we went to IMRT, then we went to VMAT, and then we started to adapt the systems in order to be able to verify the complex plans. So what we do right now is that we do a pre-treatment QA, we pass the plan, and then after that we don't do any other QA. For the rest of the fractions, we assume that everything is fine. So the second question is, why to stop there? Why are we stopping? Why don't we do the QA until the end of the treatment course? And the simple answer is that there is no device available yet to do this. So what we can do is to have an online quality assurance system. If this system existed during the Teract 25, then we would have catched the error. We would have catched the software error. We would have stopped the beam, and we could have executed on the error, could have stopped the treatment without causing any harmful damage. So this is the sense behind IQM. This. We designed the system to perform online quality assurance on the patients and to eliminate not to eliminate the errors, but be aware of the errors that may happen so we can execute on them and just have a sort of online quality assurance. So IQM is an independent, keyword independent, online segment by segment link monitoring system, which it collects the dose area product for every single segment and it compares it to a reference signal in real time. Of course, there are different models of having online quality assurance. So we can look at the log files from the LINAC and then process them, but that's not online and that's not independent. It depends on the LINAC, and also the log files are available at the end of the treatment. So you find out about the error at the end of the treatment. Or you can have a detector in the path of the beam, between the beam and the patient, that measures the fluence. Or you can have a detector underneath the patients where you measure the transmitted beam through the patient. IQM is in the detector before patient category. So we are moving from offline QA system to an online QA system because we know that if we constantly monitor the patient, the beam being delivered to the patient, then we have a better quality assurance. The quality assurance will always be there for every single segment, every single patient, all the fractions. So we are at a time where we are moving from an offline to an online QA system. And good old Yahoo Messenger reminds us online, offline. So Dr. Muhammad Islam and the IQM team members, we all thought of this. So what is the design consideration? We have to create a system that is as simple as it gets without compromising its functionality or its performance. As Albert Einstein said, makes things as simple as possible, but not simpler. The key is, as the treatments are getting complex from static to IMRT to VMAT, and the quality assurance devices are getting more complex, it doesn't mean that we need to have a very complex quality system to monitor the system. Just because the treatments are getting more complicated, it doesn't mean that the verification system has to get more complicated. So I'm going to talk about IQM system a bit more and what features it has. The IQM system has a special gradient sensitivity, and when it's mounted to the LINAC, it covers the entire projected area. It has a built-in two-channel electrometers, which collects the signal in real time and it analyzes it. We also have a 3-axis MEMS accelerometer to determine the segment boundaries for BIMAT treatments independently. We have a temperature and pressure sensor to take into account for the air density inside the chamber, which can affect the magnitude of the signal. And we have a wireless communication between the chamber and the Bluetooth transceiver there. And a battery management system. So the IQM system consists of an ion chamber, a single large ion chamber, and it composed of 2 polarizing electrodes sitting at -500 volts and a central plate sitting at 0 volts. So by doing that, we change the amount of air between the electrodes, and by changing the amount of the air, we change the amount of the ionization, therefore the amount of the magnitude of the signal. If you run a profile in the gradient direction, you get a signal sensitivity like this. And this signal is composed of, this sensitivity is composed of this linear region and the tails. And here, the tails are due to loss of electron equilibrium. And in the non-gradient direction, you get a profile like this. And here, we don't have any sensitivity. And if you put both gradient and the non-gradient into each other, and you create an array of matrix, you get this matrix sensitivity. And the sensitive profile is in the MLC direction, which is in the transverse direction, and the non-sensitive area is in the radial direction. So, what does the IQM signal composed of? So let's say this is my gradient ion chamber, and I'm delivering this aperture. When I deliver this aperture, IQM is the primary signal, the primary radiation. It sees the transmitted beam through JAWS MLCs here, and also the stereofocal radiation. What IQM does is that since it's a single ion chamber, it gets a single signal. It integrates all these signal components and it comes up with a dose area product. Whereas for 2D arrays, they have different detectors and different signals, and they produce isodose lines or a dose fluence map based on that. So that's the nature of IQM signal. It integrates everything from the LINAC FET. Okay, so as I mentioned earlier, IQM measures the signal and it compares it to a reference in real time. So what is this reference? Where do we get the reference from? There are 3 references. The first reference is performing... So the first reference is to measure the first fraction and have that as our reference signal for the rest of the treatment course. Or we can perform the pre-treatment QA with IQM in presence of a secondary verification system. In this case, I have IQM and ArcCheck doing a delivery at the same time. So by doing that, you get the signals, you measure the dose fluence from, in this case, ArcCheck, and if the plan is a pass, then you know that the signal that you acquired from IQM is also considered the good signals, and you can use that signal as the reference for the rest of the treatment course for that patient. And this is what it looks like when you are acquiring this reference signal for IQM. There is no tolerance, there is no corridors, because we are just looking at the signal that is being produced, and IQM is recording this as the reference. The other reference that we have is the calculated signal. And the calculation, we can compare the measured signal to the calculation in real time. Or what we can have the calculation and measurement hybrid, which means that when you deliver the first fraction, you compare it to your calculated results. And then if you make a judgment that that plan is a pass, then you can use the measurement from the first treatment and have that as your reference for the rest of the treatment course. So, this is IQM, this is the mentality behind it, it's how it works. And now the question is, how does IQM integrate to the clinical workflow? If you introduce the IQM system in your clinical workflow, how does it integrate? How does it fit? So we have all these generous beta testers, and we welcome our latest research partners at Korea and Japan. We give them the IQM system, they are testing it, and if they want to introduce it in their workflow, how does it fit? So IQM, it fits with it covers the entire treatment flow. So it goes from treatment planning system to the LINAC. So it integrates with the treatment planning system, the workflow, and the LINAC. So how does IQM integrate with the LINAC? The current clinical workflow, you do a treatment planning system. You come up with the dose distribution, you optimize, you calculate the signal in the treatment planning system, you have a DICOM file. You send that DICOM file into a record and verification system, and when you're treating the patient, the LINAC control system calls for that DICOM file and you deliver it. That's without IQM, that's what we do right now. But when we have IQM in play, what happens is that when you have that DICOM file from the treatment planning system, a copy of it goes into IQM database, and IQM database is a calculation based on that. The IQM application here. The IQM application here, it helps. It's in constant communication with the IQM database and the dosimetry of the IQM. So when you are delivering a beam, the electrometer is integrating the signals. And in the case of MIMAT, you are getting the in-kilometer data and you're defining the segment boundary, so the signal per segment. IQM application is automatically acquiring that data and is comparing it to a reference that has been stored in the database in real time. How does IQM fit in the clinical workflow? Well, we did simulate the impact of IQM and assess the impact of IQM in the clinical workflow. So this is the current clinical workflow we have. We do a patient imaging, MR, CT, PET, we superimpose the images, we come up with the dose target volume. And then based on that, we determine the GTV, CTV, and the PDV. And we do an inverse planning, we do an inverse treatment planning calculation, so that is dose optimization. We send that DICOM file or that plan into a treatment verification system, and we perform a quality assurance on it. If the quality assurance passes, we go with the delivery of the field to the patient. If it fails, as shown by the red arrows, we either repeat the quality assurance procedure or we go all the way back to the treatment planning system to see where the error came from. This is what it looks like when you have IQM in your workflow. It may look complicated, but it's really not. So up until here is the same workflow, except when you get to the treatment team model. That's because IQM is made of 3 aluminum plates. Each of them are 1.5 millimeter thick. So you are going to have beam attenuation. That needs to be taken into account when you are calculating for the beam. So when you do a treatment planning system with the IQM beam model, you export the DICOM to the IQM database here, and you store it in the IQM database. You go on with the rest of the workflow. You import the plan into a record and verify system, which is constantly talking to the monitor application. You have seen the demo. And when you want to do plan QA assurance, there's an offline beam monitoring system. So when you're running the beam, you get automatically the IQM calculated signal or from the treatment planning automatically. And when you're doing a dose delivery, you can do an online beam monitoring system verification. So I'm just going to walk through the workflow. Up until patient imaging, no IQM involved whatsoever. In the beam model, so for the beam model, you have 2 options. You can either go and then do the entire beam model measurement, so that's the profile, those curves at different depths. And when we did this at PMH, we saw that there is not much difference in terms of the beam behavior. The depth dose curves are looking pretty similar. The beam quality hasn't changed significantly, it's all fine. And the profiles for the center region, they are between 0.5%. And for the outer regions, it's 1% because the plates are attenuating the lower energetic part of the photons that are being attenuated. But the most useful part of the beam is at the middle central 20 by 20. So why not come up with a simplified beam model? And a simplified beam model can take into account for the tray factor and the field size factor. That's very simple. You know what the attenuation of the IQM system is. You put that as a tray factor, and then all you need to do is to perform a series of square field measurements with different size, normalize them to a 10 by 10 to come up with your field size factor. And that's what we did. We used this simplified beam model approach, and to test it, we calculated a signal and treatment planning system for a SBRT beam. And as you can see here, this is a snapshot of the dose distribution and the dose volume histogram generated by both beam models. And the IQM beam model is represented by the dash curves, and the clinical beam model that we have is represented by the solid curves. And as you can see, they are pretty much lying at the top of each other. There is no significant difference. The maximum, minimum, mean, and standard deviation for both those volume histograms calculated by both beam models is pretty much the same. So it's promising. You can integrate into the IQM into the beam model by just doing one simple measurement, and that's the field size factor. So that's for treatment planning system. And record and verify system, IQM just communicates with the record and verify system. And now we go to plan quality assurance. So before we do the actual treatment, of course all of us perform a pre-treatment plan QA. And and that's how the IQM software looks like when you are doing a pre-treatment plan QA. And you're acquiring your signal here, and you have an expected signal, your ref, and I say the ref can be measured, calculated, or a hybrid of both. We did that for IMRT beams, IMRT SBRT beams. And we delivered 33 segments, total of 33 segments for 5 fractions. And we take it into account for the variation in the LINAC output. And if you look at and if you compare all your fractions compared to your first fraction, which is your reference, you see this percent differences with respect to the reference. And as you can see, they are within plus minus 1%. That's the reproducibility, that's the accuracy of IQM in the IMRT beams. So, the total number of 132, that's 33 segments for 5 fractions. The total number of segments that were out of the plus minus 0.5% were 5 out of 132 segments. So IQM signal was accurate to within plus minus 5% for 96.2% of the times. That's the reproducibility of IQM's framework. Dose delivery. So this is actually a video during the online beam monitoring. It's a video that I made while I was doing this experiment. So here you have the IQM application in a standby mode. It's communicating with the LINAC, as shown at the bottom corner. The door status is closed. IQM is in the monitoring status. The battery, the voltage of the battery is defined. The electrometer and the inclinometer are also working okay. So when you call up the beam, as you saw here, the patient was automatically picked up by IQM system. That's user interaction free. When you call that patient, the IQM application goes searching the database. It says that, okay, for this patient, John Smith, that's being treated right now, I have this reference. I'm going to grab this reference, and I'm going to do a measurement, and I'm going to compare them in real time. So what you see here is an SBRT beam being delivered, and IQM is monitoring it and is comparing it to its reference in real time. In this software, I used the plus minus 3% tolerance, dose tolerance, and I also used the 3-point running average. There can be uncertainties in the beam delivery and the beam monitoring. So in order to manage that, we performed a 3-point running average. And as is indicated by the yellow bar there, that is a single segment that is out of the plus minus 3% tolerance. At the bottom, you see the cumulative dose. So it's a graph of the cumulative dose, and that's between plus minus 1%. On the left bottom side, you see the MLC apertures as defined in the DICOM file. IQM knows about it because it gets that DICOM file from the treatment planning system. And on the right and the left side, here in the table, you see that IQM has a reference signal and a measured signal. It's comparing them. It's coming up with a delta and a percent deviation with respect to the graph. I'm just going to fast forward this video until the end. And this is the end of the beam delivery. You got 3 segments out of 120 segments that are out of the tolerance. So 117 out of 120, that's the percent pass. So as I mentioned, I performed the 3-point running average to manage the uncertainties in the beam delivery and IQM monitoring. But there has been concern that if I do a 3-point running average, is that going to hide the errors? We have 2 types of errors. We have a systematic error and we have a random error. The systematic errors are composed of, there can be an MLC bank miscalibration, MLC bank, or it can be a machine output. Whereas the random errors can be something wrong with the MLC motor or MLC stuck. So here, what you see is the 5 fractions I delivered for a particular SBRT lung patient. And for the 5 fractions, you have in average 117, 118 segments in the plus minus 3%, and the other segments are in the watch levels. So they are above 3%, but they are lower than action level, which is the 6%. So this is the reference with no errors introduced. What I did was I introduced the 2 millimeter bank error. So I opened up the field by 2 millimeters, just to see if IQM is able to catch it with this running average. So this is another lung SBRT patients, and here I have no errors. And as you see, there were 119, 116 segments between the plus minus 3 tolerance. What happens when I introduce that error, the 2 millimeter error? And now you see a series of failed segments, yellow and red. In here, you drop from a percent pass of 119 out of 120 segments to 31 segments passed out of 120 segments. So that's been clearly detected by IQM. How did ARC-check do? So I was performing this measurement as I showed in the picture with the IQM mounted to the linac head and the ARC-check set up at the ISO center. I did this measurement and ARC-check was able to detect it as well. It went from a 98-99% pass to 25.9% pass. Next error I introduced was the 1 millimeter error bank. So here, for the reference, I had 106, 110 segments out of 120 passing, and once I introduced that 1 millimeter error, you see that there are a series of failed segments in the middle there. And that is 87 segment pass out of 120. So you were up until 94, 97% pass, and suddenly you drop down to 75% pass. So something is wrong. What did ARC-check do? ARC-check was also able to detect it. Perfect. The percent pass decreased from 96%, 94% to 46.3%. Next error I simulated was an energy error. So I changed the treatment energy from 6 MV to 10 MV. This is the reference, as you can see. The 117, 116 segments passed out of 120. And you introduce an energy error. These are all with the 3-point running averages. Right at the beginning, you see you have segments in between the action levels saying that something is seriously wrong. And throughout the whole thing, you can detect the energy change. And what happened? You were having 117, 116 segments out of 120 passing, and by introducing energy change from 6 to 10 MV, you went down to 2 segments passing out of 120. And this is the ARC-check results. ARC-check was also able to detect it. Here, I introduced series of random MLC errors. This is the reference, 116 and 117. And now, when you have random MLC errors, so I simulated MLCs being not being at the correct position, is modified the RTP file, and the pass rate decreased from 95% to 85%. For ARC-check, it decreased from 99 to 94% to 86.5%. So, what are the conclusions? First conclusion. Why did we do this? Because we wanted to have a better quality monitor system. We didn't see why we should stop doing the planned QA before the patient. Why don't we all just do it until the end of the treatment QA? The treatment course. And that's because we didn't have a system available. Now we have a solution. In terms of IQM performance, I also explained how IQM works. This is a gradient sensitivity, what the IQM features are, how the signals are generated, what is the nature of the signal. I also explained the different types of references we can use, so that can be either your calculation, your first measure, or a hybrid of calculation and measurement. And I also described modifying the beam model for IQM, and I explained that we can go through the whole entire beam model measurement, but we don't necessarily need to do that. Why we need to do that when we can come up with a simplified beam model, just to introduce a tray factor and a field size factor. And finally, I also showed how IQM functions when it's monitoring the beam. And when we set a tolerance with a 3-point running average, it doesn't hide the errors, and we are able to detect it. So I compared this IQM system with other equipment tools that we have right now for pre-treatment QA. If we are able to detect the same errors as other devices, so this means that IQM is able to detect the errors, and we can just simply put it at the head of the linear accelerator, easily calculate it, have it in the beam model, do the calculation, and perform the real-time quality assurance in real time for the rest of the treatment. Every single segment, every single field, every single patient, for the rest of the treatment delivery. And this is my second last slide. So the more distance we look into the past, the further we can see into the future. And that's exactly what we did. We looked into the past, the radiation incidents that happened, and that enabled us to have a better vision, vision for the future of the patient safety. And that was in our mind. We kept that aim in our mind to enhance the patient safety for the radiation treatment for the future. Thank you very much for listening to my talk. I am willing to take any questions. Hello. I hope I didn't bore you. Thank you.
Even I learned something. It was great. Thank you very much, Makan. Thank you. Yeah, any question to him? I think he's going to stay around a little bit longer, and so in case you want to ask details. But I think that was exceptional. Thank you.
Thank you.